Hi, everybody. My name is Derek Paulson. I'm from University of Madison, Wisconsin, and today I'm going to talk about Sparkly, a TF-IDF blocker for entity matching. To begin, I'm sure that most of you know what entity matching is, but just in case you aren't aware, a quick refresh. We have table A and B on the slides here, and in entity matching, we simply want to find all of the records across these tables that refer to the same real-world entity. In this case, this record here and here refers to the same person. Continuing with our example, typically how this is done in practice is in two steps, blocking and matching. Here we have a simple blocking rule, which is that we only consider pairs that agree on the state. This gives us 4 pairs, which we can then feed into a matching algorithm, which may be rule-based or machine learning-based. And then we get 2 final predicted matches from this pipeline. In this project, we're just focused on the blocking step. And over the last 30 years, there have been many different solutions that have been developed. These range from simple sort-based all the way to complex deep learning-based solutions. There have been multiple great surveys that have been published recently, and I'll refer you to those for a more in-depth background. In any case, many of these solutions have been implemented both in industry and academia, and a few examples of such systems are up on the slide here. Much to our surprise, though, TF-IDF blocking has received virtually no attention that we're aware of in recent literature. This is despite the fact that it's very well known in IR and web search for document similarity, and we also found it to be highly promising for our initial experiments. So in this paper, we want to do an in-depth study of blocking using TF-IDF to see how it would perform. And we were very shocked to find that we were able to outperform 8 state-of-the-art blockers and scale to hundreds of millions of tuples. And we've pushed our solution into production in industry. Now let me tell you about our solution, Sparkly Manual. Suppose we have 2 tables, A and B again, which have these records pictured here. We're first going to construct a TF-IDF index I on table A, and then for each record in table B, we consult index I and get the top K values. So if we take a V1 here, for example, we're going to consult index I. This will give us 2 records output from table A, which is going to be U1 and U2. We're going to collect all of these top K results into our candidate set C, which is our final blocking output. Zooming in a little bit on how we compute TF-IDF scores, suppose that table A has these 5 attributes pictured here. We're going to start off by asking the user to manually identify a small set of blocking attributes to be used. Suppose they select these 3. If we take U1, for example, these are the 3 attributes selected for blocking. We'll take those, pre-process, concatenate, and tokenize them into 3 grams to convert U1 into a bag of 3 grams here. We'll do a similar process for V1, again producing a bag of 3-gram tokens. Finally, to compute the score between U1 and V1, we'll apply the BM25 algorithm over the bags of 3 grams, where BM25 is just a scoring function in the family of TF-IDF scoring functions. Of course, we want to scale this up to many records, and we do that by using common open source software, in particular Spark and Lucene, hence the name Sparkly. Suppose we have a 3-node cluster. We have a driver node here, which is N1, and 2 worker nodes, N2 and N3. We'll again begin by taking table A, building a Lucene index on it, and then distributing that index I to all of the worker nodes' local disks. We then take table B and chop it into pieces and send each piece over to a particular thread on a worker node. With the nodes that we used in our testing, there would be about 16 threads running, so we're running all these chunks in parallel. Zooming in on just this chunk here, we're going to consult the local copy of index I to get the top K results. Again, if we take V1 as an example, we're going to consult index I. This gives us two records from table A, which is U1 and U2. We're finally going to collect all of these top K results back into our candidate set C, which is our final blocking output. As described here, we have a system that does top K blocking on a distributed shared nothing architecture. And we have specifically chose this architecture to maximize our throughput. Now, with this architecture, probably the first thing that comes to mind is what happens when I gets particularly large? What happens if it doesn't fit into the worker nodes? Fortunately, this isn't a problem for most cases. Even when table A is 10 million tuples, I is only 1 to 2 gigs. It takes 20 to 30 seconds to distribute, so that's perfectly manageable. However, in industry, tables can get much larger than 10 million, often 100 million or up to 500 million tuples. And to deal with these large data sets, we break table A into multiple chunks and run them separately. For example, if table A is 100 million tuples, we could split it in two to get A1 and A2, which are both 50 million tuples. We can then run A1 versus B and A2 versus B and combine the results back together to get our final blocking output. By doing the splitting, we can ensure that Sparkly never builds too large of an index and therefore scale to hundreds of millions of tuples. Now we've already gone over how Sparkly Manual works, but again, as a quick refresh, we have these attributes in table A. These are manually identified as a small set, which we then concatenate and 3-gram tokenize. And then we use the BM25 algorithm on those bags, which gives us this scoring function here. Now, this is nice in its simplicity, but in some cases, it's not practical to ask the user for manually identified blocking attributes. This can be because the attributes have opaque names, or the table can be very high arity with 30 plus attributes. So to handle these cases, we developed Sparkly Auto. And what Sparkly Auto does is automatically identifies the attributes and tokenizers to be used for blocking. If we suppose we've run this algorithm and we get name with tokenizer T1 and city with tokenizer T2, our scoring function is going to become the BM25 score using T1 on the names plus the BM25 score of T2 on the cities. The goal of this automatic solution is to find the combination that maximizes the recall or the percentage of gold matches in our blocking output. And there are two major challenges to do this. First, we don't know what the gold matches are since we don't have any labeled data. And second, there's an exponential number of matches or combinations for us to consider. We give a detailed explanation in the paper on how exactly we address these challenges, and I'll refer you to that for more details. Moving on to our evaluation, we experiment on 21 data sets. 15 of these are popular entity matching data sets that come in 3 different flavors. We have structured, which is typical relational data, textual, which has most of the content in a single textual attribute, and dirty, which is relational data with missing attributes or misspelled values. These data sets cover a wide range of domains and range from a couple thousand all the way up to 1 million. We also have 3 large scaling data sets that go up to 26 million, and then 2 numeric and 1 highly textual data set that we ran to evaluate how Sparkly would behave on such data. We use these 21 data sets to compare against 8 state-of-the-art blockers. We have 2 deep learning blockers and 1 traditional rule-based blocker that was published in VLDB 2021 that was shown to give a state-of-the-art accuracy on entity matching tasks. We also compare against 3 hash-based blockers from JetAI, which is a popular open source Java library for entity matching. And finally, we have two top K-based blockers, which are Jacquard and Cosine. These are included because they were shown in recent work to give very good results on a wide variety of tasks, so we compare against those as well. To compare against these methods, we take a look at both the output size, or the candidate set size, and the recall of the candidate set, which is the percentage of the gold matches produced by the system. To start off, we're going to look at our comparison with the deep learning-based blockers. On the top left here, we have Amazon Google structured. On the x-axis, we have the recall as a percentage. On the y-axis, we have the candidate set size ratio also as a percentage. The candidate set size ratio is simply the percentage of the cross product that we're returning as our candidate set. Now, with these axes, down and to the right means that we are producing high recall with a small candidate set size. So down and to the right is better. If we zoom out and take a look at the red line, which is Sparkly Manual, we'll see that we outperform both deep learning solutions on all data sets that we tested. Moving on to hash and rule-based blockers. On the top here, we have 3 Jet AI methods and the union of rule-based blocking and deep learning, and Sparkly with a different K values set. For each of these, we report the candidate set size and the recall. And what we found is that Sparkly consistently achieves both high recall and a very predictable candidate set size, while in contrast, other methods in some cases do achieve high recall and a reasonable candidate set, but are overall much less predictable, in some cases producing a very poor recall or an unexpectedly large candidate set. Moving on to Jacquard and Cosine, we find that Sparkly is either the best or comparable to the best on all the data sets that we tested. In some cases, we outperform Jacquard and Cosine by a pretty large margin. We, of course, ran many other experiments for this paper, and I'll summarize a few more key ones here. We found that Sparkly Auto outperformed Sparkly Manual, and while both scale with respect to dataset size, Sparkly Auto is much faster. Sparkly Auto can also be practical on many real-world entity matching problems. We were able to block 10 million tuples in under 100 minutes on 10 nodes for less than $13, and we got similarly good results on 26 million tuples. We also found that Sparkly can outperform current blockers on highly textual and numeric data, but it can be extended to do even better since it's not currently tuned for such use cases. Informally, we also ran 180 million tuples on 100 AWS nodes in about 24 hours. And we compared against TopK using OpenAI embeddings and found that we got comparable or better recall, but ran much faster with a significantly smaller index size. In conclusion, we think that TF-IDF blocking needs a lot more attention in research, especially given the results that I presented here today. Sparkly can already be practical on many real-world entity matching problems, but there's, of course, always plenty more work to be done, and I'll refer you to our paper for a detailed discussion. Sparkly, we think, also provides a very strong baseline for future work to compare against, and such future work should seriously consider using Sparkly's architecture or something similar to it. In particular, TopK blocking on a distributed shared nothing cluster. We give this suggestion because we found that it can significantly improve recall, scalability, and predictability of the system. For more information, please see our GitHub homepage, read our paper, and with that, I'll say thank you so much for attending my talk, and I will conclude here. Thank you.